Thank you. So thank you for having me here. So I will be talking about an idea of using topological information of the large-scale structure data to infer cosmological parameters. So some of you may have seen an earlier version of this talk where I describe how we use similar methods to study quantitatively phase transitions of statistical systems, such as identifying order parameters and deriving critical exponents, and using these methods to study some structures or discover some structures of the landscape. So in this talk, I will focus on applications to cosmology and highlight some new results we find this year. Now, a challenge common to different scientific areas is to effectively infer from complex higher dimensional data space, the underlying theory. The first thing we may want to do is to discover some informative patterns. Now, suppose somebody give you this data set. How would you describe it? You are too quick. So a complete answer is that there are 100 points with some given coordinates, right? So this is a correct description, but didn't say much about the structure of the data, right? So a more informative answer, as Jesse already told you, is that this is a noisy circle sample from an annulus, okay? So this less complete answer may actually teach us more about the structure of the data, okay? As I described, data has shapes, and the shapes of data can inform us about the physics behind. The question is, how do we strike a balance between completeness and effectiveness? Now, this is, of course, what summary statistics are for. In designing summary statistics, there are different metrics that you may use. We would like the summary statistics to be informative, interpretable, and robust to noise. At the same time, we would like the computations to be fast and scalable. Okay? So oftentimes, these metrics are competing with each other. So the question is, how do we find summary statistics that are just right? Okay? Now, one extreme is to just do without summary statistics and design a very powerful machine learning model on high resolution simulations, okay? Or to have a lot of data collected from different ways experimentally. But then the burden is shift to having to generate a large number of high quality simulations and to design machine learning models that could capture and retain the important informations of the data. So coming back to cosmology, which is the main focus of this talk, thank you, Ben, for the 4-slide crash course on cosmology, so that I don't have to repeat some of the terminologies here. So a central goal in cosmology is to reconstruct the initial conditions of the universe, as well as various cosmological parameters from the data, for instance, from the large-scale structure measurements. An outstanding question is whether the initial seed of structure formation is Gaussian or is weakly non-Gaussian, as the theory of inflation would predict. Now, one can, of course, design a machine learning model with map-level inputs. So you have lots of simulations at the level of the maps, and then you train a machine learning model that tries to learn about these cosmological parameters. But a more conventional approach is to work with the endpoint statistics and use them, endpoint correlations, and use them as a summary statistics. So the lowest order correlation is a power spectrum. The next order is the bispectrum, and so on. And as I argue in this talk, persistent homology captures the topological information of the data set and provide a set of informative, interpretable, and robust statistics. Now, for some cosmological parameters, persistent homology may provide a more competitive measure. And it is also computationally less expensive to do machine learning inference on this topological statistics versus doing machine learning inference with map-level inputs. Now, anytime when you derive summary statistics from a data set, you lose some information. So with the ever-increasing power of machine learning, can we simply do without summary statistics? So here I've shown you some n-body simulations of the large-scale structure of the universe with different levels of non-Gaussianity. So these nonlinear parameters tell us how non-Gaussian the initial conditions are. So on the left is minus 250, and on the right is 250. Now you can see that even with exaggerated level of these nonlinearities that are already ruled out by experiments, it's rather difficult to tell these simulations apart at the map level. So some cleverly designed summary statistics may allow us to tease out rather subtle signals from the data. So the question that you may ask is, why topology? So why would you expect topology to provide a competitive measure of primordial non-Gaussianity? And the reason is the power of locality. So the main difficulty in detecting primordial non-Gaussianity from the large-scale structure data is to disentangle the non-Gaussian features that are generated by late-time physics from those that are generated in the early universe, say by inflation. So thanks to the accelerated expansion of inflation, quantum fluctuations that seeds initial fluctuations are stretched outside the horizon, leading to some apparently non-local correlations. Now, topologies precisely probe these non-local correlations. And these non-local correlations that topology can probe could not be altered by late-time physics. So for instance, the nonlinearities of general relativity acts only locally. And as a side remark, these non-local correlations that can be probed by persistent homology are precisely the reasons why they can outperform standard machine learning approaches in studying phase transitions whose order parameters are non-local. For instance, if the order parameters are vortex, anti-vortex pairs, as in the case of the XY model, so it has, we have studied this, and we find that it gives a very powerful way to detect the order parameters and to derive critical exponents. So now we can easily characterize the topology of data. Jesse already gave the answer right away for two-dimensional examples. And this is the case when the dimension of the data space is small. But when the dimension of the data space is huge, we can no longer simply visualize the structure of data. So topological data analysis, or TDA in short, is a tool in computational topology that was designed to diagnose the shape of data. Now, to characterize the topology of a set of discrete data points, we need a notion of persistence. And the idea of topological persistence is to not consider a single representation, a single topological space, but rather to consider a family of topological spaces and tracks topological features that persist as we vary the parameters that label these spaces. Okay, so the intuition is that real topological features persist while short-lived features are noise. Now, TDA is widely used in other fields. For instance, they are used in imaging and in neuroscience, robotics, and sensor network. For instance, it was used in computer vision to characterize the shape of an object. So here the data would be a point cloud that is made up of points that are sampled on the surface of an object. So you would like to see what object that is. And so by sampling points on the surface of the object, you can sort of study the characteristic shapes of the object. Now, despite these applications, TDA is, to the best of my knowledge, is largely unexplored in physics. So for these reasons, we have developed TDA in a variety of physics contexts. And in this talk, I will focus on the cosmology work and especially the new results. And towards the end of the talk, I will mention some work that we have done in showing that TDA can be used together with machine learning to do cosmological parameter inference. And the punchline is, even without much effort, a simple neural network already can give rather accurate, fairly accurate parameter estimations. So Suppose not everybody here work on persistent homology or TDA. So let's spend a few minutes describing some basic ideas of topological data analysis. So many of us are familiar with the notion of topology for continuous manifolds. Okay. So for instance, the IAIFI coffee mug that I'm going to get after giving this talk is topologically equivalent to a donut, even though it's not edible. And topology roughly describes the shape of an object that is preserved under continuous deformation without gluing or tearing the object apart. And the speakers today all make heavy use of topology in their work one way or the other. However, in data analysis, we are not dealing with continuous manifolds, rather a set of discrete data points. Nonetheless, we can represent our data set in terms of something that is called a simplexural complex and analyze its topology. So what is a simplexural complex? A simplexural complex is made up of simplices. Examples of lower dimensional simplices are vertices, edges, triangle, and tetrahedra. And so a simplexural complex is a set of simplices that is closed under taking intersection and faces of elements in the set. For example, if the simplexural complex contains a triangle, all its edges, namely, all its faces, namely the edges, should be included in the simplexural complex. And in this example, there are triangles that intersect at a point, and so that vertex should be part of your simplexural complex as well. And the advantage of doing that is that the data set is represented in the combinatorial way, so it's easy to handle computationally. Now you can analyze the topology of simplexural complex by computing its homology. Now, homology is a technical term in topology, but to the computer scientists here, all you need to know is just counts the number of k-dimensional holes. The rank of the homology group is known as the Betti numbers. The zeroth Betti numbers counts the number of connected components, in other words, the clusters. The first Betti number counts the number of loops, and so on. Okay? So as an example, these two shapes can be distinguished by their first Betti number. And again, because the data set is represented in a combinatorial way, so homology calculations amounts to matrix reduction, which can, again, be handled very easily by computers. So the question is, how do we form a simplexural representation of our data? So we just have a set of data points. Where are the simplices, and what is the simplexural complex? Now, this procedure of finding a simplexural representation turned out to be not unique. It's very natural to associate a data points with a vertex, but you have to start making choices when it comes to connecting the vertices by edges, okay? Not to mention the triangle and so on. And so we would like a way to characterize the topology in a way that is stable against different choices of simplexural representation, and also stable against small perturbations of the data. Okay? You don't want the answer to be very sensitive to where the data points are when you try to read off some informative pattern from the data. Okay? So a procedure that achieves this goal is known as topological persistence. The idea is to not consider a single simplexural representation, but to consider a family of them. So you consider a family of simplexural representation of the data with some parameters that we call the filtration parameter. As you move through the filtration, different topological features may appear and they may disappear. And so we will, from now on, refer to these events as birth and death, respectively. Now, persistent homology tracks each distinct topological features. And the intuition is that real topological persists, whereas short-lived features are not. So we want to read off the long-lived features from analyzing the topology of the data. So it's perhaps, again, easier to visualize this with an example. So we have, again, our set of data points that are sampled from an analyst. And you can see how persistent homology can systematically characterize the data's topology with a sequence of simplexural complex. So we form simplices as follows. First, we fatten the points to spheres with some radius. So fatten is perhaps not a politically correct word. We supersize the points to some spheres with some radius. And so the radius of the spheres will be our filtration parameter. And we connect two vertices by an edge if the spheres overlap. And we include the triangles if all the edges are present. So this is our simplexal complex. So as we move through the filtration, different triangles and different edges are included in the simplexal complex. Some topological features appear, some of them disappear. But as you increase the filtration parameter, you see that there's a one cycle that persists. So this is what we want to read off from the data. Very good. Now, unfortunately, the way that I have just described to you of forming simplices is computationally costly. The way I construct simplices is known as the Vietorov's-Ribbs construction. It is computationally costly because we include more simplices than is necessary. And now, as we will see, in a single cosmological surveys, there are tens of billions of galaxies. So this way of characterizing the data's topology would be computationally wasteful. Turns out a much more effective way, much more efficient way to characterize the data's topology is to consider different ways of forming simplices. And this is known as the alpha filtration. I won't go into the details of explaining what this alpha complex and alpha filtrations are, because that would be a distraction. It's a lot easier to visualize the way to construct simplices that I explained earlier, except to mention that you could carry out the same computation much more efficiently while retaining the topology with a much smaller number of simplices. To give you an idea of the speed up that you could get by doing this alpha filtration, the number of simplices in a Vietorov's-Ribbs construction grows exponentially with the number of points, with the number of vertices, so that would not be favorable. But it only grows as a rather weak power for the simplexal complex that are constructed from the triangulated data. So the idea of the alpha filtration is to first triangulate the data and look at a much smaller number of simplices and form filtrations from that. And so in the case of 3 dimensions, which is of interest for the large scale structure, this growth of the number of simplices is only linear. So it's a much more computationally manageable. Now, we can visualize the persistent homology of the data with a scatter plot known as persistent diagrams. So these persistent diagrams are scatter plot that shows the birth and death of each topological features. So for instance, here I show you the scatter plots. In the x-axis is the birth, and the y-axis is the persistence, namely how long these features survive. And so in the point cloud that give us the persistent diagram on the right, here the point cloud clearly shows that there are 3 long-lived one-dimensional cycles. And so they are represented by these 3 dots here. They persist for a very long time. And the persistent diagrams turn out to be not always the most useful thing for deriving statistics and for machine learning. And so for the purpose of deriving statistics, it's oftentimes useful to process this persistent diagram to some vector space representation known as persistent images. So again, to sidestep a lot of the detail of the definitions, these persistent images are nothing but, smooth essentially smooth version of the histograms coming from the persistent diagrams, but that is obtained by binning and by introducing smoothing functions that could depend, for instance, on the persistence. And the outcome is an image that looks like this. Okay, and now this is one way to get a vector space representation of the topology of the data. So the x and the y-axis are, again, the birth and the persistence. There's another way to derive statistics from the persistent diagram, and that is you could turn these persistent diagrams into different topological curves. And this one-dimensional curves counts the number of topological cycles in specific regions of the persistent diagrams. So here I have a persistent diagram, and what I call B1, a topological curve, is the number of cycles, the number of dots on this persistent diagrams to the right of it. Okay? So they are born after a certain filtration scale. So I count the total number of them. So that would be one way of generating statistics. And I can also consider the topological curve that I call D1, the number of one cycles that die after a certain filtration scale and so on. And so the advantage of getting these topological curves is that we can derive statistics rather easily. You certainly lose some two-dimensional information of the persistent diagram, but because of the simplicity of getting statistics, we consider both persistent image, which contain all the two-dimensional informations of the persistent homology, as well as the topological curve, which are sort of reduced statistics from the more informative persistent images. Okay, so after this short introduction to persistent homology, we are now ready to apply these results to cosmology. So in an earlier work with my former student Alex Koh, we initiate the use of persistent homology in studying the CMB. And subsequently, together also with Matteo Biagietti, we extended this work to the large-scale structure of the universe. And you will see in a second why this extension is important. And this collaboration has grown into a multinational one. And in this talk, I will be mostly focusing on the new results coming from our study, including using topological statistics in doing cosmological inference. Okay, so the question that we would like to ask is whether the persistent homology of cosmological observables can help us pin down the underlying theory. So I have inflation in mind, which is arguably the leading paradigm for early universe cosmology, besides solving the flatness and the horizon problem of the hot Big Bang, is generic predictions of an almost scale invariant, nearly Gaussian spectrum of curvature perturbation seems to be in very good agreement with data. Now, these curvature perturbations are the sources of temperature and isotropies in the CMB and the density variation in the large-scale structure. Now, different models of inflation, however, could predict different patterns of anisotropy. And the taxonomy of inflation models so far has been done mostly through two of the most well-discussed parameters, namely the spectral index, which quantify the scale dependence of the curvature perturbations, and the tensor to scalar ratio, which quantifies the amplitude of gravitational waves. Now, the lowest order correlations you can extract from these fluctuations is the two-point functions or the power spectrum, oftentimes expressed in momentum space. And the deviation from scale invariance is parameterized by this number called the spectral index. And if you have a perfectly Gaussian theory, this is all you need, because the two-point correlations functions tell us everything about all the higher point correlations. But inflation is an interacting theory, so the fluctuations generated are not perfectly Gaussian. The leading non-Gaussianity is the three-point function, or the bispectrum. And yeah. So what is not always true? Sorry.
So I mean, it's not always true that the three-point function has the most signal compared to, say, some higher endpoint function or the tails or whatever. And that seems the only reason to belabor that here is because it seems like your method might be a good estimator for that sort of rare event study.
Yeah. So one point which I sort of forgot to mention in particular is not only is topological data analysis probes non-local correlations, it actually tells us something about all the endpoint functions, right? I mean, instead of expanding in order by order, lower order in the correlations, the fact that you have a loop tells you much more information than just lower point correlations. Yeah, you are perfectly right. And we would like to be able to read off not just the lower point statistics, but also the higher point correlation. And so this is a way to get a manageable set of statistics that are still computationally doable. Right, and also in theories where sometimes the three-point functions just vanishes because of, for whatever reasons, then you would have to go to higher point functions as well. Did I address your question?
Yeah. I mean, just it's not always that it vanishes. It just can be, depending on the dynamics, it can be that it has a heavy tail, and you might want to look for that.
Exactly, right.
Yes.
And yeah, so we will do a comparison later on. We'll compare how well we do compare with 2-point and 3-point functions. And so you will see that for something, it is better. And we have it because the statistics are so interpretable, we understand why in those cases we do better. But they are certainly different. And I think that's a very important point in breaking degeneracies, for instance. Okay, so the leading non-Gaussianity is the 3-point function, if it's present. And you can use scalings and symmetries, translation and rotational symmetries, to argue that this 3-point function is fully specified by its overall size, which is usually denoted by this nonlinear parameter FNL, and two variable shape functions. These are momentum-dependent functions. And so, and because of that, in comparison, these 3-point functions tell us a lot more than the 2-point functions because they give us a functional worth of information instead of just a number like a spectral index. Now, the bispectrum for general single field inflation has been computed long ago, and in fact has even been completely classified. And the level of non-Gaussianity for simple models tend to be small, but there exist models that have sizable non-Gaussianity. A prime example is dBi inflation. So let me just highlight two of the shapes in this classification. One of these shapes is the local shape, which peaks in the squeeze limit. And this has the largest signal when you look at the longest scale. And because of momentum conservations, all three momentums should fit as the side of the triangle. So this is what is called the squeeze limit. And there's another shape known as the equilateral shape, which peaks in the equilateral limit when all the momenta are equal. And so there is yet another shape that was commonly discussed, known as the orthogonal shape. I don't plot it here for a reason, because if I were to do it, you would not be able to tell from the slides that they are different. So the orthogonal shape is by definition orthogonal to these two shapes in the function space, but because it looks so similar to the equilateral shape, it would be a challenge to try to identify, to try to distinguish these two shapes with machine learning. So let me inject a personal note here. I was waiting patiently for 17 years for something like non-Gaussianity to be discovered. And I first got interested in machine learning because I was secretly hoping that with all the powerful machine learning methods, we would be able to somehow see that. Maybe not in a very straightforward way, but it's at least certainly something that we could aim for. Okay, now more complicated models can certainly give rise to more shapes. For instance, if the inflationary potential is oscillatory, as in axion monodromy inflation, the shape of non-Gaussianity looks very different. It certainly falls outside the classifications that I've just mentioned. Now, like scattering amplitudes in particle physics, these non-Gaussian shapes can help us reconstruct the interactions governing the early universe. So for this reason, this subject has been rebranded as the Cosmological Collider Program. And in particle physics, we oftentimes use different strategies to look for different types of particles. Sometimes we look for bumps in the cross sections. Sometimes we look for missing energy. So similarly, we may want to develop different algorithms to look for different shapes of non-Gaussianity. So the standard way to detect non-Gaussianity is to fit the data with templates of the bispectrum or the trispectrum that can be computed from theory. You can project, in the sense of distributions, the data onto these known shapes. However, some shapes are known to be very difficult to detect. For instance, the shapes that are oscillatory have zero overlap with almost all templates. And some ideas to detect local shapes of non-Gaussianity with the power spectrum has been developed. This is known as the scale-dependent bias. The idea is to make use of the transfer functions between the primordial power spectrum and the halo power spectrum. And so this is the primordial power spectrum On the right is the primordial power spectrum that you can compute given a theory. On the left is the halo power spectrum that you can measure. The ratio between the two is the bias, which, as you can see, is most pronounced at the largest scale for the smallest k. As you will see, because persistent homology probes multiscale topology of the data set, doesn't necessarily have to probe the larger scale. Turns out the non-Gaussian signal is most sensitive to a rather different scales. Now, we started out doing persistent homology on the CMB for reasons, because the curvature perturbations, the cosmological perturbations, are in the linear regime. So it's easier to extract primordial non-Gaussianity from the data without having to disentangle them from the nonlinearities of gravity. And indeed, the most stringent constraints on primordial non-Gaussianity came from CMB measurements from Planck. However, large-scale structure measurements holds great promise in the future. There are several reasons for that. The large-scale structure data contains a lot more modes than the CMB. They give us a three-dimensional worth of information rather than the two-dimensional information on the large scattering surface. Methods like the one that we are developing here is also expect to be more powerful because of the higher topologies that can be probed by the large-scale structure data. And indeed, some of these topological features were already implicitly used by cosmologists. They are known as clusters and voids. Okay. But as I will try to argue, these observables can only be precisely defined and identified from noisy data using persistent homology. And this systematic methods also tells us something is missing. As it turns out, one-dimensional topologies, these filament loops, turn out to give stronger constraints, at least for primordial non-Gaussianity. So finally, topology probes the tails of the initial density distribution. The fact that we see a loop means that there's a high density contrast. So we expect these topological features to be most pronounced in late-time observables because gravity amplifies this density contrast.
So, Gary?
Yeah.
I think there's something I missed, which is, it seems not to be truly topological in the sense that if you keep the process going, you eventually fill everything in.
Yes, right.
So there's a scale in some sense that you're going to have to use, or maybe even what I'm thinking about now is whether there's multiple scales.
Right.
And you take your annulus example,
yes.
You could imagine there'd be holes in the annulus at a different scale to the annulus.
Yes.
So how do you know a priori what scale to sort of stop and start at?
Right. So maybe it's easier to explain with the CMB. So in that case, it would be a temperature map. So the filtration is the temperature. So we know from the experiments that delta T over T is 10 to the minus 5. So if you vary the temperature too much, you are going to fill up everything. So that sets the scale. And so when we say long-lived features, we're comparing with that physical scale. So in the case of density perturbation, it would be the density, typical density that you are trying to identify.
Very good, thanks.
Any other questions? All right. So now, in real life, when we are looking at these cosmological surveys, there are lots of tens of billions of galaxies. So scalability is very important. And so a lot of what we did in our work is to make this computation scalable. So one of these ways to make the computation scalable is to use this alpha filtration, but then there's a lot more that we said in the paper, but maybe I won't go into the details of that. Now, before we study how different cosmology changes the data's topology, we should perhaps ask what's the typical scale of these topological features that we are after. So from the persistent diagrams that I've shown here, we find that the typical scale of these topological features, whether they're clusters, filaments, or voids, are of the order of 10 megaparsecs, which is much smaller than the size of the observable universe. So one conclusion you can draw already is that if you use persistent homology to probe non-Gaussianity, you are probing a different scale. Instead of probing the larger scale, you're probing something of the 10 megaparsec scale. Now, this typical scale of the topologies they're dominated by statistics around 10 megaparsecs. The fact that they are mostly of the 10 megaparsec scales allow us to divide the simulations into many sub-boxes. And we can compute persistence within each of these sub-boxes without having to worry about boundary effects. And so we would then subsample this persistent homology. We would then subsample in each of these sub-boxes with a uniform halo number. And so this division and subsampling is not only speeding up the computation greatly, but it also allows us to account for the variations of the halo numbers across different realizations of the same cosmology due to cosmic variance. Yes. Yeah.
So is this to realistic numbers or is this not? Do you go to something like 10,000 or so? Would this also work or not?
Yeah, yeah. So this is just one example. Okay, so as I said earlier, it turns out filament loops give us the most competitive observable, but you don't know a priori that this is the case.
Could I just ask,
yeah.
the plot that you showed, which where does this come from? Are you doing this on n-body simulations?
Yeah.
Is this halos? What is the lower, like what is the smallest mass of the halo? What's the size of the n-body
so this is at the dark matter simulations level, not the halo level. But later on, when we study Fisher information, we do take into account halo and all that. So this is not what you would immediately want. This is the dark matter distribution, and then you would then run with your halo model to get the actual galaxy distribution. But since we are comparing apples with oranges, right? We are trying to compare different methods of the same simulations. We are not too bothered by the fact that this is not yet the real thing. But so we're trying to compare how well it does compare with the power spectrum and the bispectrum. Okay, so what we did is to develop an end-to-end package to analyze the topology of the large-scale structure data. And so we can, to see how well this method performs, we can quantify the probability of detecting an anomaly, in this case, a non-Gaussianity, by counting the fractions of data points that lies beyond 97.5% confidence level of the chi-square distributions of some baseline cosmology. So the baseline here is a Gaussian theory. So you're comparing Gaussian simulations with non-Gaussian simulations. And for detecting non-Gaussianity, it turns out that the best statistics come from B1, counting the number of loops as a function of the coarse graining scale. And the detection rate was found to be slightly better than using halo bias. So the anomaly detection rate for, say, FNL equals to 10, I've given some numbers here. So now anomaly detection is easier if we know what we are looking for. And an important question is whether we can resolve the degeneracies of different cosmological parameters, since they can give rise to similar topological features. So to address this question, we have carried out Fisher forecasts for different shapes of non-Gaussianity and the cosmological parameters in the lambda CDM model. Okay, so in different colors, it shows the 1 and 2 sigma contour plots for analysis based on persistent homology from the power spectrum and the bispectrum and from the combined statistics. And so these plots here are already marginalized over halo occupation distribution parameters. So we find several interesting features. First of all, the constraints from persistent homology are generally a little tighter than the constraints coming from the power spectrum and the bispectrum. Not by a whole lot, but a little bit better. And this can be understood. I think that was the comment made earlier, because persistent homology contains information not only about lower point correlations, but all the higher point correlations. Secondly, the parameter degeneracies, as shown by this contour plots here, indicates that they are mostly different from the power spectrum and the bispectrum combined. And this is because they are probing different scales. One is probing larger scale. For instance, one is probing, say, 10 megaparsec scales. And this aspect is important for breaking degeneracies when you combine the statistics. So you do a lot better by combining what we did with persistent homology with the usual statistics that you come from power spectrum and the bispectrum. And finally, we find that the statistics derived from persistent homology are stable against HOD uncertainty, halo occupation distribution uncertainty. And this is, again, explainable because of the topological nature of the observables. Things are not too sensitive about these uncertainties that we have. This table shows the one sigma Fisher constraint on different shapes of non-Gaussianity and for the cosmological parameters. I'd like to draw your attention to the Fisher constraints on the shapes of non-Gaussianity, and Eva may find that interesting. We find that persistent homology gives slightly tighter constraints on the equilateral and orthogonal shapes. In comparison, the constraint from persistent homology on local non-Gaussianity is less strong compared with the power spectrum and the bispectrum. And this can be understood with our interpretable statistics. So local non-Gaussianity, as I explained, peaks at the squeeze limit, and therefore it probes the larger scales. Whereas persistent homology, most of the statistics derived from persistent homology comes from topological features of the order of 10 megaparsec scale. So if local non-Gaussianity peaks in a different kinematic regime, you don't do as well as other shapes of non-Gaussianity. Whereas for equilateral or orthogonal shape, the signal will show up strongly at different scales. So when you can use your topological features at the 10 megaparsec scale to constrain this parameter, you can do better. And most importantly, it's not about the absolute value of these different constraints. They were done on a much smaller simulation volume. You expect better results to be obtained if you go to the bigger simulation volumes. But the point is, you can get better constraints if you combine the statistics from persistent homology and from the power spectrum. So in the last few minutes, right? Okay, 1 minute, 2 minutes, okay. So we have gone a little bit better from human intelligence to artificial intelligence. We were interested in the questions whether we can train a machine learning model on these persistent images to sort of tell apart different cosmologies. So the idea is the input would be persistent images. They can be generated by simulations. They don't need to be of very high quality, high resolution, because as you can see, we are probing most of the statistics come from 10 megaparsec scale. So you could feed these persistent images to simple machine learning models, such as a neural network, and try to see whether you can infer cosmological parameters from them. And so this is what we did in our recent ICML paper. We focus on two cosmological parameters, omega matter and sigma 8. And we use a fast simulators known as FlowPM to quickly produce snapshots of the late time distributions of the dark matter particles. And FlowPM is a fast simulator, so the simulations produced are not of high resolution, but they're accurate enough for our purpose. And we use the Rockstar Halo Finder to identify halo in the dark matter in the simulations. And that generates for us a lot of halo catalog. And for each halo catalog, we can compute persistent homologies. And the summary statistics are the persistent images. Okay? So we can design a machine learning model with the persistent images as the input. And so we did that with a very simple neural network that combines in parallel a CNN with a stack of dense layer. And without much effort, we seem to find reasonably good cosmological parameter estimations. So the input would be the persistent images. They are the 0, 1, and 2 cycle persistent images. The output are the two cosmological parameters that we want to find. And we find a mild improvement in inference precision using these parallel networks, combining these two checks, then to just using the CNN alone, 10% improvement. And finally, we conducted a parameter recovery test to compare our machine learning inference model based on persistent images with the standard Bayesian inference on the power spectrum and the bint persistent diagrams. I think Ben called this explicit Bayesian inference. Okay, so we find that our machine learning inference model based on persistent image outperform slightly than this two standard Bayesian inference models. And we also find that persistent statistics, all these topological statistics, give us better information than the power spectrum, independent of how we do our parameter estimation, whether you want to do it with Bayesian model or you use the machine learning model. Okay. So let me summarize. I hope I have conveyed to you that persistent homology provide us a set of informative, interpretable, and robust summary statistics. Their computations are fast and scalable. And in comparison to the power spectrum and the bispectrum, persistent homology can give competitive constraints on cosmological parameters, including primordial non-Gaussianity. And in comparison to the power spectrum and the bispectrum, the advantage of doing persistent homology is that it probes non-local features. It tells us a lot more than lower point correlations, and sometimes it can probe different scales. And this means that when combined with other conventional summary statistics, we can get tighter constraints on cosmological parameters and break degeneracies. So now there's also a very interesting connections to the renormalization group story that was extensively discussed yesterday. So it turns out if you look at the latent dimensions, it was found that the topology in the latent space gets simpler and simpler as you go from layer to layer. So there's some kind of renormalization, some kind of cross-graining that's going on. And finally, we have sort of illustrate how you can learn from topology by training a very simple machine learning model, neural network model, we can perform cosmological inference. And so let me just stop there. Thank you for your attention.
Thank you very much, Gary. You're running very late, so I'll take one question and then I'd say we can continue over lunch. Happy to surrender you. Okay.
So, I mean, thanks for the really interesting talk. So people have presented Fisher forecasts for maybe it's other methods recently, comparing it with what is expected from this mega mapper, and using the so-called effective field theory large-scale structure. And I think the output of that analysis was something like a 2 or 3 times improvement. And I'm wondering, and then that's this method that sort of parameterizes our ignorance of short scale physics quite extensively to be conservative. You might expect machine learning to find features that sort of packaging in terms of a EFT expansion and momenta isn't very good at. But basically, my question is, you had a forecast here. You mentioned that larger volumes would do better. Are you in a position to make such a forecast, including those, not just one, but the many so-called bias parameters that enter in the EFT language? How would that enter here, and like what your forecast would be, or would that take longer? Yeah, I mean, we hope to do it, but we are limited with human manpower. So it would be good to do a side-by-side comparison. I mean, with the same kind of computing resources and same kind of volume of simulations and all that to see how well it does. But we take this as an indication that it could do somewhat better in some aspects. And especially when we compare simulations of the same precision and so on, it outperforms other methods. So I think it's an invitation to people who, say, for instance, generate simulations and do data analysis to study more, to generate more of the simulations for us. So for instance, one of the bottleneck for us, we would love to do cosmological inference, not only on sigma 8 and omega eta. We would like to be able to do that for non-Gaussianity. So the question is, can we generate very quickly a large number of maybe not so high resolution simulations, accurate up to 10 megaparsec scale, and try to see how well we can do. I would love to do this. Yes.
Ben, can we do this over lunch?
Yeah, but we need. So, for instance, I was glossing over it. We will need a range of FNL. Right, so Quixote, for instance, give us some leverage on doing this problem, but we would like to be able to vary FNL over, So we would like to have many, many persistent images. So we would have to have many values of the value of F and L to be able to feed the machine learning model to learn these features.
All right, let's continue the discussion over lunch. Let's thank Gary and also Sergey again for the nice talks, and we reconvene at 2.